Okay, welcome back everyone to Markov. I'm really sweaty and gross because I'm in a closed up small room with no windows, door closed so you don't hear my dogs, 5 computers running, and a lot of protective equipment so that this guy doesn't gouge my eyes out. This is Azrael. She is a monkey-tailed skink from the Solomon Islands, which are near Australia. And I hope she's just gonna hang out there and not cause me problems. A new homework was just posted today, and yeah, I don't know, not much to say about that. So check it out, and on Friday in class, we'll talk a little bit about it, maybe some hints for getting started on any ones that you might be having trouble with. But today, we're going to talk about classification of states of a Markov chain. I told you last time that the reason you should care about this is because there's going to be lots of results coming up about when Markov chains kind of reach an equilibrium or if they do. And all of those are going to be based on a setup like, well, if they have this property and this property and this property, then yes, they do. Okay, so we are ready to go. We are classifying states. So I call this part classification of the states of a Markov chain. So I'm going to start with a definition for you. A state I, we say that it can be reached from or is accessible from state J if you can get from I to J. And I mean something really specific about that. So can be reached from or is accessible from state J if there exists. I'm going to start using more math notation, which most of you are quite familiar with, but I know some of you aren't. So we write this kind of with a backwards capital E. If there exists an integer n greater than or equal to 0, such that the probability I go from I to j in n units of time is positive. There may exist many such n, but we need at least one. So we can get there with some positive probability. And it doesn't have to be directly and does not have to be 1. Okay, so that is the definition of can be reached from or is accessible. So next up, I have another definition for you, and it's just saying that if state I can be reached from state J and state J can be reached from state I, we say that the states communicate. Oh, and by the way, let me finish the previous definition. We're going to write I arrow J. And by doing that, it makes it a lot easier for me to write the second definition. So if we can go from I to J and we can go from J to I, then we say that they communicate. So communication in Markov chains is always a two-way thing. And if you are reading Duret, it's going to look like a one-way thing. But then you'll notice that he only uses it after he's grouped states into classes where every state in the class you can go from every state to every other state. So he doesn't say you can go backwards, but in that class, you can go from every state to every other state. So you can go both ways, but Duret does not look like he's saying it's both ways. And so we write a double arrow, not a double arrow, a double-sided arrow. So if states I and J communicate, then the number of steps we have to go forward and back, the N for the definition of accessible, it's probably going to be different in each direction. So this means we can find an integer n and an integer m such that we can go from I to j in n steps with positive probability and j to I in m steps with positive probability. Okay, so I did say that Duret was putting these in classes, and we can put these in classes of states that communicate because this concept of communication forms what is known in math as an equivalence relation. And that means it satisfies 3 properties. So communication is an equivalence relation, and that means precisely the following 3 properties are going to hold. First, I, because I know it's lagging, so I'm writing I, there's a reflexive property And before this can make sense, I do need to back up to my original definition and point something out. I'm going to scroll back. In my original definition, note that n is greater than or equal to 0. The equal 0 is really weird, but it's kind of an artifact that makes things nice, much like we define 0 factorial to be 1 because it makes things nice and come together. So this means that a state always communicates with itself. So you might have a state in a Markov chain, and if you look at the transition matrix, you will definitely leave on the first step with probability 1, and you will not be able to get back there. But we still say that I communicates with itself just because we're allowing for 0 steps, which is totally artificial, but part of the definition. And so that's how we get this reflexive property, because what this means, i.e., it means that a state I, any state I, communicates with itself. And so in order to get this, we just need to take n to be 0, which again is kind of artificial, but part of our definition. Then we have a symmetric property. So it is symmetric, and this just means if I communicates with J, then J communicates with I, and that's totally by definition because communication means you can get from one to the other and back. So you can get from the other one to the first and back. So this just says, i.e., if I communicates with J, then J communicates with I, and this is purely by definition. Okay, so the third one is the transitive property of an equivalence relation. And this says that you can just sort of kind of transfer things along. So if I communicates with a state J and J, I don't usually write, I mean, I don't have the best handwriting, but trying to rush and not have too much dead time, making this pretty bad. But I still got a lot of feedback from a lot of you that like it because it gives you time to write rather than me just blasting slides up. So, okay, so the transitive property says if I communicates with J and if J communicates with K, then I communicates with K. This one I want to prove, and I only want to prove it because it doesn't seem like there's anything to prove, which is part of the problem with a lot of things in this course. It's just like, of course, if you could get from I to J and you can get from J to K, then you can get from I to K. Like, what is there to show? But if you had to show it formally, I would prove this using the Chapman-Kolmogorov equations. So if we can go from between I and J and K, this implies that there exists integers n and m greater than or equal to 0, such that, so that's my little st, such that we can go from I to J in n units of time with positive probability, and we can go from J to K in the remaining in another m units of time with positive probability. It actually means more than this. It means there exists 4 integers because I do need to be able to go back, but I'm only going to do kind of half of this proof. So there's actually 4 different integers that exist given the setup of this problem. And so, so the Chapman-Kolmogorov equations, I claim that I can go from I all the way to K in n plus m steps. And again, it might seem super obvious, but here's how you show it. So the probability to go from I to K in n plus m steps, by Chapman-Kolmogorov, you can sum over an intermediate state. I already used K, so I'm going to use like L. That's a curly L. I can go from I to L in the first n steps, and then I can go from L to K in the next m steps. And that's running over all L in the state space. But one of the L's that's going to be hit in there is J. So that's just a single term here. Okay, so this is Chapman-Kolmogorov, and then continuing on my bottom line here, this is greater than or equal to P I J N and then P J K M, because that is just a single term in there. The rest of the terms could be 0 or not. That's why it's greater than or equal to this. And this is purely greater than 0 by our given assumptions. So we've seen that if you can go from I to J and you can go from J to K, this is how you actually prove, even though it's painfully obvious, how you can go from I to K. And you also need to finish this off, which I'm not going to do, but you need to show the reverse because this really isn't about getting from I to K, it's about going both ways. So we need to show the reverse in order to finish off that proof. Again, we showed that we can go from I to K because we showed the existence of an integer, namely n plus m, where we can get there with a positive probability. And again, you need to show the reverse or you haven't shown full communication. So if you've seen equivalence relations before, you know I'm going to talk about equivalence classes next. And that is that we group the states of a Markov chain into classes that are equivalent in the sense that every state in each class is going to communicate. So our version of equivalence classes are really going to be called communication classes. And equivalence relation allows us to partition the state space into what are known as equivalence classes. And in our specific context, because that's a very general statement, we're going to call them communication classes. Okay, so if two states communicate, they get put in the same class. And if they don't, they're in different classes. And again, Duret only seems to be talking about communication in one direction, but he talks about it for an entire group of states. And he says, if you can, in this group, go from any state to any other state, then they communicate, because any one to any other one means you can go back. Let's do an example. And I just want to state first that two states that communicate end up in the same class. And also, I want to say that it may be possible to move from one class to the other, but never back again. Because if you can come back again, then really those two classes should not have been separate because everything in them communicates. So it's possible to go from one class to another, but not back again, or they would have been one class to begin with. Or they would be one class. This will make more sense when we do the example, but one more thing I want to define before my example is that a Markov chain, so this MC is Markov chain, is said to be irreducible if it can only be composed, like there's only one communication class. If there is only one class, otherwise we say that it is reducible. And this is one of several things we're going to need in those upcoming theorems that I was telling you about. We kind of just, you don't have to write this down, but because it's not going to make any sense at this point in the notes. But if you start at time 0 at like any point in the state space and simulate forward, like you have at time 1, a certain probability of moving here, but maybe the next time around with new uniform random numbers, you're going to move somewhere else. But if you simulate for a long time and go out here to time infinity and end up at some state, I kind of care about whether if I start this again from the same point or any other point and collect the endpoint and collect the endpoint and collect the endpoint. I didn't leave myself space here, so let me move this over. That if I made a histogram of these, they're kind of building up into some sort of shape. Maybe, maybe not. If they do build up into some sort of consistent shape, we say, you don't have to write this down now, but we say that the Markov chain has a limiting distribution and that it is independent of the starting state. And so for theorems that say things like when this exists and when it's unique, the setup for all of these theorems is going to say, suppose the Markov chain is irreducible and other things we're going to define today. So, okay, the example, I put this off long enough. So I got a state space with 1 through 5, 2, 3, 4, 5. And I did want this to be written out ahead of time, but I didn't manage it. So here is my, you know what, let me put in a 0 as well, because I need to show a couple of things. So 0, 1, 2, 3, 4, 5, and then 0, 1, 2, 3, 4, 5. And I'm going to put some numbers in here. Oops. And as far as you trying to copy them down, the values do not matter. It's just that some of them have positive probabilities in them. So 0, 1, 2, 3. So if you don't catch the actual numbers, that's fine. But the first row, starting from 0, I can go to 0 and I can go to 2 and nowhere else. And I'm going to make that probability 2/5 and 3/5 and make the rest of these 0. In row 1, I'm going to say that I can go to 1 and I can go to 3, but nowhere else. So those probabilities are going to be 1/2 and 1/2. 2, I'm going to go from 2 to 0 and 2 to 2 with probability 2/3 and 1/3. 3, I'm going to go to either 1 or 3 with probabilities 1/5 and 4/5. 4, I'm going to allow myself to go to 0 and 1 and 4 and 5 with equal probabilities 1/4, 1/4. And then they end 1/4, 1/4, and 0, 0 in the middle. And 5, I'm going to go anywhere. So 1/6, 1/6. They don't have to be equal. 1/6. Maybe I'll cut up the last two in a different way, like 1/12 and 3/12. I think that adds up to 1. But again, the actual numbers are not important. Okay, so we want to find all communication classes. So I would just start with, right now we're doing kind of a brutish approach, a brute force approach. I do have another slicker way we can do this that I'm going to write up but not talk about in this class or test you on. And that involves making an adjacency matrix, which is really similar to this probability matrix, except that it has ones and zeros, and it has ones if you can move from one state to another. So this is just find communication classes, just a brute force sort of thing. I'm going to start a set, and I'm going to put my first state 0. And then I'm going to look at the matrix. So from 0, I can go to 0 itself, which is really not interesting because 0 always communicates with itself, whether or not you can actually go there. But I can go to 2. Now, 2 should not be in the communication class if once I go to 2, I can't get back to 0. But because of this, I can see that I can go back and forth between 2 and 0. So 0 and 2 are in the same communication class. Okay, so actually, if you just focus in on the 0, 2 stuff and ignore the 1 row and column, you can see that 0 and 2 only go back and forth between each other. And I actually can't reach any other any other state when starting from 0 or 2 because the rest of the probabilities are 0. So I'm going to close off this class and start another one. Okay, so let's look at the next state that we haven't classified yet, state 1. This is a pretty easy to read matrix. If you look closely, you'll see that state 1 can only go to 1 and 3 can only go to 1 and 3. So there's another 2 by 2 thing. 1 communicates with 3 and we don't go anywhere else. Okay, from 4, I can go to 0, but we've already established that from 0, we can't go to 4, or we would have put it in the first class. Okay, so from 4, as I was saying, I can go to 0, but we already established from 0, we can't go to 4. So that's why it didn't end up in the first class. And we already established that 1 and 3 can't go to 4. But looking at the 4th row, we can go to 0, 1, 4, and 5. And looking at the 5th row, we can go from 5 to 4. So I can see that we can move between 4 and 5, and those guys communicate. And 5 is not going to communicate with anything else, or we would have picked it up already. So we're done. Now, if we couldn't, we have 3 classes. And if we did this and we only had 1, everything communicated with everything else, the chain would be, the chain would be called irreducible. But we have a reducible chain because we have more than 1 class. And these states and the classes they're in, they are classified as either recurrent states or classes or transient states or classes. Recurrent states or classes are ones that if you start there, like at a state, you will return eventually. Maybe in a long time, but you will return in finite time. And transient states are ones that if you escape, you will never return again, that there is a chance that that will happen. So 0 and 2 are recurrent, which I need to define. The recurrent states, which I have a formal definition coming up later when I have some more notation, i.e. starting at either one, you definitely will return eventually, even though it might take a long time. I think the easiest way to look at recurrence is not transient. And to figure out what a transient state is, you need to exhibit a positive probability of escaping the class, never to return again. So starting with either one, you will come back, and then by the Markov property, you're going to come back again because you're going to start all over. But again, the easier way to say this is not transient, because if you look at, oh, by the way, we call the class recurrent as well. The entire class, which is the set 0 and 2, sorry about my dog. 1 and 3 are also recurrent states, because if you look at this set, there is no way to move out of that set. If you moved out of that set, you could not come back, because otherwise those two sets would have been one communication class. So there's no way to move out of the set 1 and 3, because if you look at the matrix, the 1 and 3 can only alternate between each other. So 1 and 3 is also a recurrent class, or individually the states are said to be recurrent states. But 4 or 5 is what we call a transient class, and those are individually transient states, i.e. there is a way. Doesn't mean you're going to leave, right? From 4, going back to the matrix, from 4, I could go to 4. Okay, I got another question that I'm going to answer after I finish what I was saying about this transient state, because I think it will make more sense there. So looking at the matrix, state 4 is transient because there is a way to escape, never to return again. So because we can go from 4 to 4, or also 4 to 5 and back to 4, it doesn't mean that you're going to escape right away. You can just spin around 4 to 4 to 4 to 4 to 4 hundreds of times. But if there's some positive probability of escaping the class, then we say it's transient. And there is, because here's one of them. I can go from 4 to 0, and yet 0 is in a kind of closed class with 2. So once I hit 0, I cannot return to 4. So there is a way to escape, never to return again. You should always say it dramatically somehow. Never return again. So for example, we can go from 4 to 1 in one step, and that's an escape. That I said 0 before, but 1 will also work. And then from 1, we can't get to 4. So let me write that using our notation. I'm going to say, and 1, the line for communication, but crossing it out. From 1, we cannot get to 4. For all my life in Markov chains, I've never been a fan of directed graphs, which everyone uses, and I'm very happy if you use it as well. The reason I'm not is because, I don't know, I think they just get so messy. But if you were to list the states, and I think they're hard to read when there's a lot of arrows. This is state 0, 1, 2, 3, 4, and 5. Please, by all means, do it. So we can go from 0 to 2, and we can go from 2 to 0. We can go, I'm going to use another color. We could go from 1 to 3 and 3 to 1. We actually can also go from 0 to 0 and 1 to 1. Now I'm making a real mess out of this. And 2 to 2. Okay. So if the chain is irreducible, actually, let me back up. If a state is recurrent, you will come back. And we will, you know what, I can prove this to you. So we will prove that recurrence and also transience are class properties, meaning everything in the class has to have the same designation. And we can do it, it's pretty simple, using Chapman-Kolmogorov. So I'm going to prove that either the end of today or the beginning of tomorrow. If you have one communication class, meaning the chain is irreducible, everything moves to everything else, then everything has to be recurrent or transient. If you have a finite state Markov chain where everything communicates, then everything has to be recurrent because there's no escape. So if you have an infinite, I need to just write examples. Let me write these facts down. So one, here are some facts. One, if the chain is irreducible, so that means one big class, then we say that the entire chain is recurrent or transient. Then, so this is one big class, then the entire chain is recurrent or transient. And the second thing is if the entire chain is irreducible and the state space is finite, the chain is irreducible and the state space is finite, then it's definitely recurrent because there's no place to escape forever. And the state space is finite, the chain is definitely recurrent. So how can you have an irreducible chain? Like I can go from anywhere to anywhere else and yet have a transient chain, which means I can escape a state forever with positive probability. Don't write this down next because I will be writing this down eventually formally, either today or tomorrow. But an example would be my favorite random walk on the integers, both positive and negative. And if you go up one, say you're starting at 0, if you go up one with probability p and down one with probability 1 minus p, no matter what state you're at and no matter what time step you're at, we will prove that if p is 1/2, the states are recurrent. By the way, with this scheme, everything communicates in theory. You can get from any state to any other state. So it's irreducible. So if one state is recurrent, the entire chain is recurrent. And so we can prove that if p is 1/2, this is going to be recurrent. And as you might expect, if p is not 1/2, it's transient. So like if p is greater than 1/2, it's going to drift off to positive infinity. And if p is negative 1/2, it's going to drift off to negative infinity, meaning starting at a state, there is a positive probability of not returning. So that's an example of an irreducible chain that could be transient. But if it's irreducible with a finite state space, there is no escape. And it's always recurrent. So I want to prove these things, but I do need to set up kind of a more formal definition of recurrence and transience and some notation. So I've got a couple of definitions for you here. The first is the first hitting time of a Markov chain to a state. So you have a Markov chain, and we say that the first hitting time, and this is a little bit different than a first return time, which I'm going to define next. So this is a first hitting time of a Markov chain on state I. We're going to denote it, although we're going to use this for both, because everyone does, as a T sub I. And this is going to be the minimum time step n greater than or equal to 1, such that, not true, greater than or equal to 0, such that xn is I. So it's just saying, given a Markov chain, what is the first time you hit state I? If you start there at time 0, then you've already hit it. The hitting time can be 0. And then we have the concept of a first return time, which means that you started there and you do return. So this typically uses the same notation, but I'm going to add a little more to the end. So it is the minimum time n greater than or equal to 1. So that's the difference, such that xn is I. By the way, this is the first return time to state I. And this is kind of conditional. It's when you start at I. These are random variables. Yeah, thank you. Very good point. We want to talk next about their distribution and the expected values. And these are going to be how we define recurrence. We're going to define recurrence to be a state is recurrent if the first if the first return time is finite with probability 1. And so we're setting these up for definitions. But yeah, they're random variables. All right, let's do it. let's use our notation. So I'm going to throw my pen really far away. Okay, so this is the formal definition of recurrence. I'm going to let TI be the first hitting time at times greater than 0. It's really this, but if I don't condition on starting at I, then it's not really a return to anything. It's a first hitting time, but not allowing time 0. So I'm not going to call it anything. I'm just going to write the minimum n greater than or equal to 1. The 1 is important for this definition, such that xn is I. So this is going to be a first return time to I if we start at I. And I'm going to let little gi be, first I'll write it in English and then with some mathy notation, be the probability that starting at I, the process will eventually return. And what this means in terms of our new notation, so formally, this is the probability that the first hitting time on state I at times greater than 0, that this is going to be finite given that we start in state I. And as a notation thing, since we're going to be writing this kind of thing a lot, you could write this as the probability that T sub I is finite, and then put a little subscript on the P, and that means that you started from I. So that's just notation for this. And also, if you want to find the expected value, let me move this over, it's not going to fit. If you want to find the expected return time, given you start at state I, another way to write this is expected value with a subscript I, TI. And this maybe makes more sense when we want to start at I and find the expected number of steps until we hit state J, because there's too many I's floating around here. But this I subscript is where you start the chain. Okay, so here's our definition for recurrence and transience. State I is recurrent if this G sub I is 1, and transient if it's less than 1. And transient if it's less than 1. State I is transient if G sub I is less than 1. That's the definition. Can't fit it in. Next time I will start off by proving that transience and recurrence are class properties. This was the question that came up before. And what that means is within a class, all states are transient or all states are recurrent. So we can use this to prove that. We now have like a framework. So let me just say in the moments I have left, you are going, this is a good time, screen. Okay, you are going to return to a recurrent state infinitely often by the Markov property. Starting at state I, recurrence means you will eventually return. By the Markov property, you're starting at I again. Recurrence says you will return. Markov property says actually you're going to return infinitely often. But recurrence alone doesn't say anything about the speed at which you'll return. It might take a long time. The expected time to return could actually be infinite, even if the probability you will return is 1. In that case, we're going to break down recurrence into more classes. Within recurrence, which ones do you return to fast and which ones not fast? Transient states you're eventually going to leave. So next time, we're going to derive a formula for given you are at a transient state, what is the expected number of times you return before you are lost forever? And then I'm going to try to come up with some real life problems where you would care about something like that. So I'm out of time. Thank you. Azrael says thank you. Uh, Moses is really mad. I'm not picking him up. Bye.